Hello Prof, we are Group 1 and we will be presenting on our machine learning project. These are the content we will be going through today. The aim of this project is to provide a robust predictive model to predict the health outcome of horses. We managed to achieve top 6% in the ranking. Let's take a look at the insights from the EDA. The target variable has 3 classes and there is an imbalance with 50% of the data belonging to the leafed class. Both categorical and numerical variables contain missing values. Further analysis is needed to determine the best strategy for imputing these missing values. We first analyze the dataset by plotting the correlation matrix. From the matrix, we can conclude that pain, rectal temperature, and surgical lesions emerge as strong predictors of health outcomes. We dive into numerical variable analysis by plotting pair plots. We concluded that variables shown above show meaningful differences among health outcomes, suggesting that they could be strong predictors. Whereas some variables such as hospital number and ID do not appear to provide significant distinctions between the outcome groups and may not be useful for model training. Lastly, all three lesion variables show similar distribution with most values being concentrated at low levels, which shows no significant distinction in outcome. For categorical variable, we observe an extreme class that appears only in the training data. For the feature pain, there were extreme classes with similar meanings but different names, which increased the difficulty of prediction. Hence, we considered renaming them. For features that do not have inherent order, we will use one-hot encoding. For features with inherent order, we will encode them manually to preserve the sequence.
After exploring the data, it's time to pre-process it and do some feature engineering. Firstly, we drew box plots for numerical variables to check for outliers. We found two variables which contained many significant outliers. However, further analysis suggested that these higher values may be related to the target variable, which is useful for prediction. Therefore, we did not perform any transformations on these variables. We also conducted label encoding and one-hot encoding for categorical variables so we can capture different relationships more accurately. Next, we needed to handle missing values. Numerical values were imputed with the median, while categorical variables were either imputed with the mode or a suitable default value. For example, the default value in abdominal distension should be none rather than the mode moderate. Finally, we removed columns which contain mostly of zeros, as they will likely not provide much valuable information for model fitting.
Now, let's take a closer look at the models we tested for this task. The random forest classifier is an ensemble model that builds on multiple decision trees. Each tree is trained on a different subsets of the data and uses randomly selected features. When making a prediction, the model combines the results of all the trees through majority voting to determine the final outcome. We fine-tune these hyperparameters to maximize the model's performance. Some key features of the model include bootstrapping, where each tree is trained on a different subset of the data, adding diversity to the model. The random selection of features also help reduce the correlation between the trees, making the model more robust. Finally, the prediction is more reliable as it is determined through majority voting across all the trees. LightGBM is a fast, efficient gradient boosting model optimized for large datasets. It handles class invariance by adjusting parameters like scale post weight, helping the model focus on minority classes. Unlike traditional level-wise growth, LightGBM grows trees leaf-wise, expanding the model promising branches to improve predictions accuracy with fewer trees. Here are some key parameters we use for baseline. LightGBM builds each tree by focusing on the residual errors of previous ones, gradually correcting them to improve performance with each iteration. It includes L1 and L2 regularization to prevent overfitting by penalizing the model complexity. Once trained, LightGBM aggregates predictions from all the trees to make the final classification, enhancing the accuracy. Next, we will discuss his gradient boosting, an optimized version of gradient boosting for faster computation and better efficiency for large datasets. It bins continuous features into discrete intervals, reducing split points and minimizing memory usage, which speeds up training and handles high-dimensional data efficiently. These are the optimal parameters obtained through randomized search. Here are the key features. It uses gradient-based optimization, where each tree corrects the errors of the previous one, improving the predictions iteratively. It bins continuous features into discrete intervals, which reduces the number of split points, speeds up the computation, and improves memory efficiency. Finally, his boost supports L2 regularization and parameters like max depth and learning rate to prevent overfitting.
We further experiment XGBoost where it builds an ensemble of decision trees sequentially, where each new tree corrects the errors made by the previous trees. Unlike simple models that fit the data once, XGBoost iteratively improves its prediction by minimizing a specified loss function through gradient descent. These are the optimal parameters that we use for the XGBoost model. Here are some key pointers. XGBoost uses gradient boosting whereby it is designed to optimize model performance by sequentially improving upon previous runs. L2 regularization is also used to control the multiplicity of the model, whereas max-depth and subsample helps to control tree growth and introduce randomness, ensuring that the model generalizes well to unseen data, making it less likely to overfit. XGBoost also support parallel processing, which speeds up tree construction. Lastly, XGBoost have a built-in cross validation, which can help improve model performance during training. Next up is CatBoost, which is a gradient boosting algorithm designed to handle categorical features directly, eliminating the need for explicit encoding in the data pre-processing process. It constructs models incrementally by adding decision trees that correct the errors made by previous trees. This gradual process allows it to build an ensemble that effectively minimizes prediction errors. One of CatBoost's key strengths is its efficiency in managing high cardinality categorical variables, making it suitable for datasets with many unique categories. The optimal parameters obtained through randomized search are shown here. The key feature of CatBoost is that it is designed for efficient handling of categorical data without needing one hot or label encoding. CatBoost also uses ordered boosting, which respects data order to reduce bias in predictions. Additionally, CatBoost builds symmetric trees where all leaf nodes at each level share the same rule, speeding up execution and reducing overfitting. CatBoost also uses L2 regularization on leaf values to prevent overfitting and improve model generalization. Finally, we tried using the ensemble methods to combine multiple models to boost predictive accuracy. This utilizes the strengths of each model to reduce both variance and bias in predictions. There are a few key techniques for aggregating these models. First, max voting, which picks the class label with the most votes across models. Next, averaging, which simply averages each model predictions. And finally, weighted averaging, which assigns weights to models based on their performance, allowing stronger models to have more influence on the final prediction. In our approach, we use the weighted averaging method. This method allows us to assign different levels of importance to each model based on its performance. The models we used for this ensemble were XGBoost, LightGBM, CatBoost, and HISBoost. By combining these models, we aim to leverage their individual strengths for a more accurate and robust final prediction. In our experiments, we tuned each model using randomized search to maximize accuracy based on cross-validation results. We then used Optilna weight class to identify the optimal weights for each model in the ensemble. Our performance metrics was the F1 macro score, which is evaluated on the validation set. Additionally, we stored out 4 predictions for each fold, helping to refine the weight distribution across models. The optimal weights for each model is shown in this table.
Moving on with our experimental analysis, we have chosen LightGBM as it used one of the highest validation accuracy and micro average F1 score. These are the parameters we choose to tune to find the optimal parameters. During training, we observe a sharp decrease in validation loss over the first 20 to 40 boosting rounds. This decline slows down and stabilizes at around 100 rounds, indicating a potential sweet spot for the model performance. However, after approximately 120 boosting rounds, the loss begins to rise again, suggesting that the model may be overfitting beyond this point. The plot displays how validation accuracy varies across different hyperparameters combination. We see clusters of accuracy around 0.73, suggesting that some combinations were more effective than others in improving model performance. After further exploration, these are the optimal hyperparameter yielding the highest accuracy. Feature importance analysis reveals that lesion 1 and hospital number are the two most influential features, offering a significant predictive power for the model. This insight is valuable for understanding which medical factors most impact model predictions, especially in LightGBM, where focusing on high importance features could potentially enhance the predictive score. In our chosen solution novelty, we want to address class imbalance. Our approach of smart plus stomach links combines oversampling with dataset cleaning, removing noisy samples to reduce bias and improve class stability. For feature selections, rather than just using a static approach, we implemented recursive feature elimination. Leveraging on LightGBM's feature importance matrix, we set a threshold to remove the least important features, reevaluating the model after each iteration to ensure the optimal feature selection. We also customize our early stopping strategies to optimize training efficiency. Rather than just using a fixed number of rounds, training stops when either the difference between training and validation loss becomes very minimal or validation accuracy fails to improve beyond a specific percentage of boosting rounds. In our comparison, LightGBM achieved a higher validation accuracy of 80%, outperforming our ensemble XGBoost, CatBoost, and HISBoost. LightGBM was also more time efficient, requiring only 115 minutes, while Ensemble took longer due to multiple models being trained. Several factors contributed to the Ensemble underperformance. LightGBM may be better suited to our dataset, which is relatively small, making the Ensemble prone to overfitting. Additionally, a well-tuned single model like LightGBM might effectively capture essential patterns, making additional models redundant. So this experiment essentially shows that a single optimized model can sometimes outperform a complex ensemble, highlighting the importance of model selection based on data characteristics. Next up on our conclusion. Therefore, LightGBM gave us the highest public score ranking at top 6% of the leaderboard. As part of our reflection, we developed and explored a range of machine learning algorithms, including random forests and others. Each algorithm offered significant strengths and unique strengths. XGBoost and LightGBM excelled in handling high-dimensional data, while random forests provided valuable interpretability. To further enhance accuracy and address individual model limitations, we applied a stacking technique combining the strengths of each model to achieve improved predictive performance. This project has been an insightful journey, offering a deeper understanding of the trade-offs between model complexity, interpretability, and also accuracy as well.